All right, welcome to I think it's our sixth edition of 40 Minutes of Competence. The pressure in a city water main is 50 psi. The pressure lost through piping, fittings, and the water meter can be ignored for this exercise. What is the height above the water main above which the water will not flow? And it's given that 1 psi is equal to 2.31 feet of water. And let's remember that right now. 1 psi is equal to 2.31 feet of water. So what we're looking at is we're looking at a situation where we have, typically we have a reservoir. That reservoir is then we're gonna have a pumping station. We're gonna take out water. We're gonna have some kind of pump here. We're gonna take out water from that reservoir. We're gonna bring it up to a top of a hill, and then we're gonna bring it up even higher. And then we're gonna store it in a tank. And it's going to be at some level like this. And then that tank obviously has some structure to it. And then we're going to just use gravity to let the water come out of that tank and go into a building. And when it gets into a building, we're going to run it up to all the floors. Maybe there's even a penthouse, a hose bib on the roof. So at different floors, we'll have takeoffs, and from those we can tap off and get some water. Now the amount of pressure in the pipe is kind of what we're concerned with. And you can see intuitively, there's like three different things to understand. And one is intuitive, one is kind of intuitive, and one takes a little bit of mental acrobatics to get your head around. But you can see kind of intuitively that if we have a tank up here, and that water is going to be pushing down and then coming back up, we can see that water seeks its own level. And so there's going to be some point right here that the water is going to stop. So even if there was an uncapped pipe right above that point, we could look in and we could see the water, but it wouldn't be gushing out in our eye when we tried to look at it. It would just be kind of there because the water would reach its own level, just like it would if I had a tube right here and I filled it with water. All right. So that, I think that's kind of the first thing, and I think we can kind of understand that. The second thing to grip is that we can create pressure when it comes in the building down here. We can create pressure, and that pressure is a function of how high that water tank is off the ground. I'm sorry, above the fixture. So whatever that distance is, that's going to affect it. So there'll be a lot of pressure down here, but there'll be less pressure here, and there'll be less pressure here, and so forth. That's a little bit harder. And then the third part is a little bit counterintuitive, but it doesn't go straight from some amount of pressure to zero up here, where it stops, where water seeks its own level, but rather the pressure increases as it moves down, and then as it moves back up, it gets less and less and less and less and less until eventually it hits zero. And so as we move up the building, we're actually going to be reducing pressure. Now this mode of supplying water for our buildings is a municipal system, and it's what many of us are on. It looks something like this, and so if the water level is up here, and if here's our fixture down here, this distance here is called the static head, and that distance is going to dictate how much pressure is in the system. And again, we're ignoring friction, which does have a countervailing effect. Likewise, we could have, for instance, well, if we don't have enough pressure, we can add some pumps, either at the municipal level, or if we have too much pressure, maybe we have a valve, a pressure reducing valve. But we're going to come into our buildings. From the point of view of our buildings, we're going to come in at a certain amount of pressure. And if we need more, sometimes we're even going to have pumps. Usually there's two for redundancy, and maybe a tank. And so that those pumps are going to fill up a tank, and that tank is going to be pressurized, and then it's going to go up. So we may have an upfeed system like that. Or of course, we may draw the water from a well and then just bring it in. So it may not come from a municipal system at all. And we've all probably seen situations where we have a tank on top of a building. And so the tank on top of the building then has what's called a gravity downfeed system. And again, we're going to kind of branch off. But just like we saw before, the lower floors are going to have significantly more pressure than the upper floors. All right, so now what? Well, when we're talking about those tanks, we're talking about something like this. In New York, you've seen these kind of giant pickle barrel tanks that feed the water below them. So what we're talking about here, and we're talking about here, we're given that there are, well, let's see what we're given. Let's go back to our question. So you see we're given the pressure in a city water main is 50 psi. And we're given that 1 psi is 2.31 feet of water. So we're already kind of told that from the municipality we have 50 psi. And psi, of course, is a unit of pressure in pounds per square inch. And the question is, how high can that go up in this building before it no longer has any pressure, that we could, be staring down at it from above in the uncapped pipe and it wouldn't be spraying our eye. And this kind of a crazy idea, because it feels like if it comes in the building, it should just pressurize forever, but it doesn't. It doesn't. And so we were told that 1 psi equals 2.3 feet. Now this is a bit different than the formula I gave you. The formula I gave you before, and I'll explain later why that is. But last week I gave you a formula that's pretty much the same formula, but it's written a little bit differently. But there's a reason I'm writing it like this now. So 1 psi is 2.3 feet. Now what that means, it means that for every psi we have, and in our case we have 50, we can push water up 2.3 feet. So when we get 2.3 feet up, we're at 49 psi. When we get 2.3 feet up again, we get 40. We're down to 48 psi if we were to tap into it, and so forth, all the way till it gets to 0 at some point. And the question that we're faced with is, at what point does it get to 0? All right. So at 0, we have to figure that out. So we have 50 psi, and the question is, at what point does it get to 0? Well, if 1 psi gets us up 2.3 feet, 50 psi is going to get us up 2.3 times 50 feet. And that's going to be equal to 115 feet. That's your answer. So if we are at 115 feet, or a little less than that, we have water pouring out, but really at a low pressure. And if we're at 116 feet and we're looking down into the pipe, we see the top of the water at 1 foot below our eye, but it's not spraying up at us. It's not spraying up at us. And at each, every fixture has a rating. So your water fountain may require 12 psi, and your laboratory may require 4 psi. And generally, they're going to be somewhere between 4 and 20. So it's not enough just to have 1 psi to kind of make it work. Now, of course you can make it work. We've all tried to drink out of a water fountain that didn't have anywhere near enough pressure. But if you want it to work properly, you want to make sure there's enough pressure at the fixture. And you have to recognize that in a big building, as you move up, that pressure is going to be reduced in an upfeed system. So that's our answer. 115 feet is how high we can go. Now, I'm going to have to move the timing of our 40 minutes of competence, because I think they mow the lawn every Thursday at 2:15. Yeah. All right. So what we get is we have a system. So if we were to look at it another way, we can say, okay, the top of the municipal is like another problem. And go ahead and do this on your own. Go ahead and read this and do this on your own, and then we'll meet back together in about a minute. So this is a different problem, but you may see some similarities. So in this case, what we've done is we've said, okay, we're kind of looking upstream. So we're not looking inside the building at the upfeed, we're looking kind of outside the building at the municipal system. So we have our water tank that sits above the town, and we're bringing water up to that water tank. And then we're bringing water from that water tank down to our building. And we say, okay, that distance between the fixture, let's take the fixture in the basement, right? So between that fixture and the top, we're given this time that the distance is 115 feet. And this one's a bit more intuitive because we already kind of decided that it makes sense that water wants to seek its own level. So again, we're given that 1 psi is equal to 2.3 feet of water. And given that, what we need to do is we need to say, okay, 115 feet, so for every 2.3 feet, we've added 1 psi, and at 4.6 feet, we've added 2 psi, and so forth. So what we're doing is we're going to divide this time. So to get the number of psi right here at this fixture, we're going to do 115 feet divided by 2.3 feet per psi. And that's going to give us, no surprise, it's pretty much a version of the same problem. That's going to give us 50 psi. So by raising it to 115 feet, we can create 50 psi of pressure. But likewise, if we start with 50 psi of pressure and we go upward, eventually we can raise that water only to that same 115 feet. And as we go up and up and up and up and up, the pressure is going to be reduced accordingly, just as if we picked a point, say here, and we kind of went out to here, that distance is going to be maybe 20 feet, so it's going to be significantly less in its pressure. Make sense? Great. All right, now, along those same lines, where did I come up with, why did I change it? Because originally, and I think one of the comments in the chat is that we could use, instead of 1 psi equals 2.3 feet of water, which is a weird way to write it. It's kind of a good way to think about it, though. You know, it's like it means that you can look at every pressure is 2.3 feet of water that it can push up, and every 2.3 feet of water that's above you is creating one unit of pressure. So that kind of makes sense. But the one I think I gave you in the original homework is that H equals 2.3 times the pressure, and that's one way to look at it. And the inverse 1 over 2.3 is 0.443, so often you'll also see it as 0.443 times the pressure is equal to the height, and that's what Hamid wrote in the chat comments. And the reason I decided to change it, the reason I'm using this one, is because, first of all, it's a little confusing to a lot of people anyway, when you start moving between them. But why pick that one? Because actually, I don't think I picked that one in the Amber book. But the reason I picked that one now is because if you go to your My NCARB and you click on your demonstration exam, you can see what the real exam looks like. And you'll go to references, and then you can see the different formulae. So you have a set for acoustics and electrical and HVAC and plumbing. And in plumbing, you have 1 psi equals 2.31 feet of water. So that's the way you're probably going to want to think about it going forward. Now, here's your next question, and it's somewhat related. Which pipes create less friction, copper, plastic, or steel? You may remember this from the Amber book, but you may not. It's easy to forget. So which ones create less friction? Go ahead and think about it and actually choose. All right. The answer is plastic. So plastic is smoother. You can kind of remember that. And you're going to definitely want to remember this for the exam. Plastic creates less friction. Less friction is plastic. Metal is more friction by a bit. All right. The next thing you're definitely going to also want to remember for the exam, which pipes expand most under changes in temperature? Copper, plastic, or steel? Go ahead and answer that. All right, the answer again is plastic, and it's by a lot. And this, I think, again, feels kind of counterintuitive. It feels like plastic should kind of stay the same, and metal always feels like it should expand. But plastic is the one that expands. So if you have water running through a pipe, and sometimes it's very hot and sometimes it's not, like with hot water, you're going to have to account for the fact that it expands and contracts and expands and it contracts. So plastic has less friction, which is good, but more expansion under thermal pressures, which is probably bad, although you certainly can account for it. All right, that concludes our plumbing pressure section. This is our problem for next week. So you can take a screenshot of it, or you can wait for us to email you. If you want to get on our email list, email firms@amber-book.com, and we'll get you on the list, and you'll get all kinds of stuff. Actually, we don't send too many emails, just the bare minimum you need to know what these questions are. But it says a bank shares a wall with a courtroom in an unsprinklered building. That wall must be rated to blank hours. No rating required, 1 hour rating, a 2 hour rating, or 4 hour rating. And for this, you're encouraged to use searches in Google or whatever your search engine of choice is for the building code, because we're going to consider this like a case study. This is the kind of thing you'd be able to do in a case study. You'd be able to search it. So a bank shares a wall with a courtroom, unsprinklered building. That wall must be rated to how many hours? All right, I'm going to answer one of the questions from, actually I said it's from last week, but I think this might have been from a couple of weeks ago. Someone said, how much of the exam questions are memorizing versus practical knowledge, especially in PPD and PDD? The answer to that question, it's kind of a good question. The answer to that question is most of it is not memorization. And the problem with focusing on the memorization is that even if it is some memorization required, I don't recommend memorizing, because you're unlikely to memorize the exact thing that they're asking for. However, if you understand the concepts, as you've seen in my course, I talk about this a lot. If you understand the concepts, you can get the problems even that you haven't seen before, because you get the concepts. So that kind of calculation that we just did, even that simple calculation, there are very few of those calculations. But if you understand how those calculations work, you'll be able to answer other types of questions, whether they be about pressure or something like that. All right, this is the part of the course where I'm going to allow you to unmute yourselves. Those of you who are ready to go study, go study. Those of you who have questions or want to listen to questions can kind of stick around. So thank you guys for coming to another 40 minutes of competence. This is by far our quickest one. I always kind of plan them out, but I'm never really accurate about how long they're going to take. So let me make it so that you can talk. All right, you should be able to unmute yourself. And ask a question if you'd like. Hello. Can you hear me? Oh, I'm going to have to unmute myself. Hold on.
Hello, can you hear me? Yeah, I heard you.
All right, I can hear you now.
Okay, good. So 0.423, not 0.33.
Yes, 0.433. Thank you. 0.44. Sorry, 433, right? 0.4.
Yes, correct.
Yeah, 0.433.